It's a guy with black full stack. Oh yeah.
All right, sorry I'm late. All right. Folks online, do you hear me?
Yep.
Somebody confirm? We're good? Anybody?
Yes, we're good.
Okay, thank you, Abby. Okay, so if you didn't see the Piazza post, assignment 1 should be posted now. Have any been able to access that yet? Some of you? Yes. Okay, so you can see it's pretty straightforward. We hope it doesn't take that long. I think the deadline is next week at some point. We were late in getting it out. Try to get it in by next week. If you can't, we'll be generous about just giving you another week since we were late. Okay, but I do want you to try to get it done in a timely manner, but I'm not going to be super strict about the deadline. If you miss it, ask for another week and we'll give it to you. Okay, so try to get it in next week. I don't know if it's next week. I think it's 28th. I can't remember the exact date, but it's 27th. Okay, so try to get it in by that date. Again, if you need more time, let us know. Hopefully it's okay. Has anyone tried to access the GPU clusters on Scholar yet? I gave you guys, or I asked them to give you all access. Okay, so who has access to a GPU outside of this class that they can program CUDA on? So maybe about, a third of people. So you can use those if you want. You just have to if we ask you for any kind of performance analysis or something, you need to be clear about what generation you're using, what part you're using, et cetera, because they'll differ from part to part. For everyone, and those of you that have or do not have them, you can also use the ones on Scholar. So everyone should be able to log into the RCAC machines and access a machine that has GPUs on it. I don't know we just use whatever the university is providing. I think they used to be Voltas. I think now maybe they're Amperes. I don't think they have Hoppers yet. So these are the different generations of GPUs. So the ones on there I think are pretty new, but not super new. But that's fine. For the purpose of this class, you'll be able to do what you need to do. So get us started on that as soon as you can. Questions on the assignment? All right. So we finished off last lecture. And I'm going to try to go a little bit faster today. I'm definitely going to be faster. So please stop me and ask questions as we go through this, because I'm going to try not to just go off on tangents quite as much myself. But please, ask me questions if things kind of are unclear. All right. So parallelism. GPUs live and die by parallelism. We talked about this thing called data level parallelism, which is very similar to vectorized parallelism. And the beautiful thing about data level parallelism is that if you express something in a data parallel way, you can actually exploit that parallelism in not just a vector engine, but you could also express that in like a multi-threaded way, right? Because if you have independent work, you could just spawn independent work, like an independent thread for each lane if you wanted to, instead of tying it together in the vector. So if you express your program or your loop or whatever in a data parallel way, it's very easy to take advantage of both vector type parallelism and even threaded based parallelism and just spawn off a bunch of, CPU threads and have each lane sort of do its own thing, right? There's no restriction there specifically. There is some synchronization you may have to worry about if you actually are depending on them being lockstep, but this sort of fact that your program is going to be expressed in a data parallel way is going to allow the GPU to basically do both vector parallelism and thread parallelism, which is how it makes use of all of these warps. Okay. So the number one rule about GPUs, when you're thinking about, should I put this on a GPU, is parallelism. Who's heard of Amdahl's law? Hopefully everybody, okay? This is like a fundamental computer architecture concept. Amdahl's law is basically, the core idea here is very simple. It's mostly just that, if you speed up one part of a program, then the fraction that you speed up is really important, right? So if 90% of your program you can speed up with a particular feature, right? Then even if you completely eliminate that 90%, you're still left with 10% of the program, right? So it limits the maximum amount of speed up that you can get. So if you've got a program and 50% of it is serial, and you can't parallelize it, and 50% of it is parallel, what is the maximum speed up that you could hope to get with as many GPUs as you could throw at this problem? Even if it's embarrassingly parallel, that 50% part, what's the max speed up you can hope to attain? 2x, right? Even with infinite cores, I cannot get more than 2x because I can only speed up that 50% that is parallelizable. Amdahl's law is more general than just, what part of the program is parallelizable. It really applies to what part of the program you speed up, but it's typically applied in the parallel sense, meaning like, I know that this fraction of my program has to run serially, and I know that this fraction is parallel. And you can sort of write this down mathematically. Again, there's nothing deriving this is not that hard to derive it. I encourage you to just look back at your undergraduate notes. And the sort of core idea here is that the latency of whatever, the sort of maximum gain that you can get out of this thing is going to be 1/1 minus p, where p is the fraction that's parallelizable, plus p divided by s, where s is the speed up that you get out of the parallel code. So in a CPU application, if 50% of it is parallelizable and I've got 4 cores, then basically I'm able to speed up that 50% by a factor of 4, and then my overall runtime reduces by essentially that linear scale, okay? And this is easy to derive. You basically just figure out like what is the runtime before you apply your optimization and what is the runtime after you apply your optimization. So if you don't have a parallel program, there's no sense in using GPUs. Embarrassingly parallel work that computer scientists would call embarrassingly parallel because it's very easy to find the parallelism. This is a supernatural fit because we're going to give you all kinds of threads. And if you have to work really hard to find the parallelism, it usually doesn't work that well on a GPU because there's just not enough of it. Questions on this so far? You've seen Amdahl's law written this way, right? I think this is straight out of 437. All right. Okay, so the bottom line is that without parallelism, GPUs are essentially useless. So let's do a simple program, okay? Let's actually take a look at some code and look at something that's embarrassingly parallel. So the very first program that we're going to do in the compute side is image processing. So this isn't rendering. This isn't raster-based triangle rendering. We're just going to basically go ahead and do something called a grayscale application, where we've got an input image. So you can think of this as like a big matrix of colors. Each of the colors has an R, a G, and a B value. This is naturally how colors are expressed. So for every I element, so if I look at this input array, let's pull this up so I can do this thing. Right, so the input array is this. Okay, that is the colored image, which is a 2-dimensional grid, which of course in real memory is linearized, right? Everything's a row major format. For the sake of argument. And basically for every element I, I've got an R, a G, and a B value. So some number of bits devoted to red, some number of bits devoted to blue, some number of bits devoted to green. And then as I sort of go through all of these different pixels, so each of these the 0th element corresponds to this pixel up here. Like this is I at 0, and that has a particular RGB value. And then I at 1 has a particular RGB value, and then so on, right? All the way through this input matrix. And my output, what I want to do is basically take those colors and create grayscale. So instead of having specific values for R, G, and B, I'm just going to create one value from those 3 color values that is the appropriate tone of gray to make something black and white, right? Like back in the olden days, right? When there were black and white TVs, you could still watch TV and you could still understand what was going on because it wasn't literally just pure black or pure white. There were basically shades of gray. And so what we're going to do is figure out, based on the lighting and based on the sort of RGB values that are in that source image, what is the appropriate shade of gray to make this particular picture, look this way. And there's an equation for this. It's a luminescence equation, I believe is what it's called. We'll show precisely what it is in the next slide. You essentially take basically you weight each of R, G, and B, and then you sum them together to get the sort of grayscale value. And we're going to do this, and then we're going to output array that's going to be essentially the same thing, but instead of having RGB values for all of the inputs, we're going to have just one singular grayscale value for O at 0, O at 1, O at 2, etc. And we're going to do this for every pixel in this image. So embarrassingly parallel, no individual pixel depends on any other pixel. It only depends on what the current color is for the input image. Questions on this? So this is very easy to parallelize. So essentially, we're going to have one thread compute one output element. And the output element is only going to be dependent on one input element, just its particular pixel from the input image. So the size of the input is identical to the size of the output. How many threads am I going to launch ideally to compute this image?
3 times the number of pixels.
3 times the number of pixels. Why 3 times the number of pixels? Just the number of pixels, right? So the number of threads I launch is actually going to be dependent on the size of the image, right? So this is something that we'll see time and time again as we construct GPU programs. Usually the amount of parallelism you spawn is dependent on how big your inputs are, right? Matrix multiply, classic example, matrices get bigger, you end up spawning more work. If this image gets bigger or smaller, you spawn more or less work. So GPUs would naturally be better at processing larger images or batches of images put together, because maybe one individual image doesn't give you enough threads to keep the thing busy, okay? Other questions? Okay, hopefully fairly straightforward. So why do we use data parallelism? Like I said, it's easy to build efficient hardware to capture it. Vector engines are very efficient because you can basically build this collection of ALUs that all listen to the same control signal. They all read from the same sections of a vector register file. If you've ever done any VLSI design, you probably have an intuition about this. So it basically expresses this regularity that makes it very easy for us to build compute units that are efficient because they're vectors. And it also allows us to hopefully, if we've coded the program up correctly, keep memory bandwidth busy by accessing things in nice, large, contiguous ways, right? So if I think about how each of these threads, right, there's going to be one thread for each of my input pixels, how each of them are accessing the data. If I sort of laid out the parallelism like I at 0, I at 1, etc. If I have parallel threads that are running together in the same vector, are they going to be touching adjacent data? What do you think? In memory. So this big input image is loaded in memory, right? Yes or no?
Yeah.
Yes. Okay. I mean, I sort of led you to that answer. Hopefully it's intuitive because, like, you know, if thread 0 is touching element I0, then thread 1 is touching element I1. And then if you bundle a bunch of those together, you get one big contiguous demand for memory. And then you can shove that at sort of a memory system that, you know, can handle things in a contiguous manner much more efficiently, right? What is one mechanism in the DRAM system that really loves you to access data sequentially? What's that? Banking, sort of. There's something else, though. Think at the chip level, inside the memory chip itself. Why would I want it? Who knows something about DRAM chips? Anybody? Some folks? Okay. So I've got a DRAM chip. Is it linear or is it a square? It's a square, right? Real memory, the programmer of the memory is linear, but real memory is laid out in, you know, basically a square format. So why then, if it's a square, do I care about, you know, accesses in time, accessing things that are close together in the address space? Yes.
Because you have to activate an entire row.
Right. Row buffer hits. Row hits, row buffer locality. Maybe you've heard of this term. If you haven't, that's okay. We will cover DRAM later in this class to give you some more intuition on this. But the big premise is, even if you've got no cache in your system, when I go to your memory system and I've got this, you know, rectangular square of memory cells, I have to activate a whole row of them at a time to read out anything. And if I activate a whole row, and that's bigger than just one float or one cache line, it's much wider than that. So if I activate one whole row of this thing, then it's efficient for me to read out everything that's on the row. If I activate the whole row, and let's say it's 1024 bits and I read out 32 bits of it, then all of that other stuff that sort of goes down, it flows through the sense amplifiers, and then just gets completely forgotten because I don't use it, and then I have to close that row and then go open up another one, which is an expensive process. So even if I don't exploit this locality spatially with a cache, which is maybe what some of you are thinking of, like they're all going to go to the cache at the same time and access what? What kind of thing in the cache is going to be helpful for this type of access where nearby threads that are accessing things at the same time can exploit? What's a cache feature that may be helpful here? Yes, block sizes, okay? Big wide block in the cache, right? So I only have to do one tag lookup for all of these floats that are all on the same cache block. So if I keep everything regular like this, it helps me build efficient compute units because I can make them vectors. And it helps me to make sure my memory system is usually dealing with accesses in a very regular manner, okay? And again, the programmer can screw this up. Like if I'm just a sadistic programmer, you'll see that you could write your CUDA program so that thread 0 operates on, the top left, and thread 1 operates on the bottom right, and thread 2 operates. You could do this, but like if you did it that way, your program's going to run way slower because your memory system's just going to, explode because it's not really built to deal with these kind of irregular accesses, okay? But people don't do that, right? People aren't sadistic. People think of things linearly, so this sort of maps very well to the way these are usually coded up. Questions so far? All right. Okay. All right. There's a quiz. There's several quizzes. Who's done any of the quizzes? Some folks. So if you haven't, please, start taking a look at them. We've done enough of the course material in class to do several of them at this point. If you start taking the quiz, when you start taking, there's no time, right? There's no time limit. So you can take a look at the material. If you haven't seen it yet, you can just not do it yet. But I do encourage you to go crack them open and start taking a look at them. They should be fairly straightforward. They're mostly just to reinforce what we talk about in lecture and ask you some concrete questions on it. All right. So let's talk about your very first GPU program. Now to do this, we need to talk about the thread structure. So some of you have programmed in CPU multi-threaded languages. Pthreads is sort of the very old now language. OpenMP is another one. But there's generally this concept of a thread ID. I need some identifier in my code to know what thread I'm operating on, like in the code, right? Because you're going to write one C program or one CUDA program, and then that's going to run on all the threads. So I need to make them do something different. The way we differentiate what they do is this thread identifier. So the thread IDs in GPUs are a little bit more complicated than the thread IDs in CPUs, where they're just linear, right? I have 10 processors, I spawn 10 threads, and I've got thread IDs 0 through 9, right? Simple. In GPUs, because you're spawning so many threads, they actually have a hierarchy of the way you define the parallelism. So you end up cutting your program up into these things called blocks, and we'll talk a lot more about that as this class goes on, which are essentially small groups of threads, okay? A maximum size of 1,024, okay, in modern systems. So if I had a big operation where I wanted 1 million threads, you can spawn that work on the GPU, but you can't put 1 million threads in one block. The block is meant to be essentially the unit where you want to tile things when we start to talk about optimizations, because the block is going to have very efficient mechanisms for using the scratch pad on chip. So it sort of curves you towards sort of keeping locality within the frame of a block. And then if you don't have locality, you spray it across multiple blocks. That's the basic idea. For our very first program, we're not really going to have to deal with that much, but you still have to understand how I get my thread ID, okay? Because with this basic program, we're still going to have to launch multiple blocks, because what if our image is greater than 1024 pixels? We'll need more blocks to actually, do this grayscaling of the image. If it's less than 1024 pixels, then I can just launch one block and I'm done. But as you'll see, like launching one block on a GPU is really inefficient because it can handle, tens to hundreds of blocks. All right. So the general idea is that when you write these programs, all of the threads are going to execute the same kernel code. So that is this single program, multiple data paradigm that NVIDIA coined. And each thread has its own unique thread index. The way that this gets broken up is to its block ID and then its individual thread ID. So this strange looking equation here is basically giving us what I would like to call the global thread ID. So if I launched 1 million threads in my program, TID in this little line of code is, would give you 0 for the 0th thread, and it give you 99999 for the thread at the very end. Okay. And the way that I do this is I basically have a bunch of blocks. Each of my blocks has a dimension. Let's say, for the sake of argument, my block dimension is 256. They usually end up being a power of 2 because that works out really nicely. In fact, they're usually a power of 32 or a multiple of 32 because in NVIDIA GPU, because then you'll get an even number of warps, but we'll get to that later. So I have a dimension. The dimension is set by the programmer when they spawn the program. So it's up to you to tell me what the block dimension is. This is programmable. And again, it's bounded. It can only be so big. If you try to launch something with a block that's too big, it'll just, choke and die and tell you your block size is too big. So I have this dimension, and then I multiply that by my individual block identifier. So every thread has a block ID that says, what block am I in? If I launch 1,000,000 threads and I've got, 1,000,000 divided by 256 blocks, then this block identifier is basically giving me 0 for threads 0 through 255. It's giving me 1 for threads 256 to 511, et cetera. Okay, it's telling me which chunk of this giant, what they call grid, I live in. Okay, so I have my unique block identifier and I have my block dimension. So this tells me what we call our block offset is. So how far into the program is, this whole thread block. Then within the individual thread block, I still have to figure out which thread am I. Okay, because if there's 256 of them, for example, then I need to know, like, am I 0, am I 255? And that's what this number signifies, this thread ID X. So if I launched a thread blocks, let's say I launched 1,000,000 thread blocks with dimensions of 256 wide thread blocks, what is the range? What is the potential range of thread ID X?
0 to 255.
0 to 255. Okay, it's going to be my internal ID within my individual block. What is the potential range of block dimension?
0 to 1023.
Nope. Block dimension is precisely going to be 256 or whatever I said. I think 256 was the block size. And then block ID X is going to be the range from 0 to 1,000,000 divided by 256. Okay, that's how this math works. And then I can get my thread ID. And then all of this, right, is just to get me my global ID. And in my simple program, or let's say I'm just doing vector add, then I would do something like this, where I have 2 input arrays, A and B, and I add them together. I add together the element at that input array and then store it in some C array at my thread ID. So here, all of the threads get their own unique identifier. They're all going to be touching different parts of memory side by side in this case, but we'll get to that. They'll sort of load in their particular element of A and B, and in this simple toy example, they'll add them together and then store it back out to the output element in C that corresponds to them. Questions on this? So this is different from the way you've typically computed thread IDs. No questions here? Nobody's asked me what .x means. You guys just don't care, or what? What do you think? What is .x hanging out in here? Yes.
It's gonna, like, you could define this to be in like up to 3 dimensions.
Right.
So this is only talking about just 1 dimension.
Exactly. So when I do, like, in a CPU, when I spawn, I just say, like, spawn 10 threads, right? It's a single dimension spawn. In GPUs, the program allows you to spawn in 1, 2, or 3 dimensions. Why do this? Well, because it's data parallel, it oftentimes maps very naturally to real data. For example, image data is 2 dimensions. So it's very natural to just spawn a kernel that has X and Y dimensions, and then you can just figure out the X and Y dimension of your pixel, and it very naturally, makes it easy for the programmer to see what work they're doing. Geometric data, 3 dimensions. So if it has X, Y, and Z, then it very naturally maps. So when you spawn in CUDA, and you're going to do this with these, like, funky, we'll see in a minute, you actually spawn an X, a Y, and a Z for both the block dimension and what we call the grid dimension, which is how many blocks you're spawning. And that allows you to just essentially spawn more threads, because internally everything has to get linearized anyway, right? There is no, like, 3-dimensional computing unit inside this thing. It takes these IDs and linearizes them, like, when it actually runs them. But from a programming perspective, it's sometimes more intuitive to use multiple dimensions, okay? And if you don't care about Y and Z, then you just make these 1. And then you can just do the same thing you did on a CPU and say, I want 1,000,000 threads. I want the blocks to be 256 or whatever. Okay. So you can always sort of fall back to a linear mapping if you don't want to deal with the sort of, multi-dimensional space. Yes.
Do one of these have to be a multiple of 32 for the work size?
Yeah, that's a very good question, and they don't. So from the programmer's perspective, you can launch any arbitrary number here as long as it fits within the total capacity bounds. Internally, the GPU has to deal with that. And once we start understanding how the hardware works, what it will do is it will just like waste efficiency. So if I specify a thread block that is only one warp or one thread wide, so if I made my thread block one thread wide and then I spawn 10 thread blocks, the machine will have to run one warp for every thread block because they're all going to be potentially going in different, they're all completely different, parts of the program. And they'll all be running with basically only one lane turned on and 31 of them turned off. But you don't see that as a programmer.
Yeah.
Okay, the programmer doesn't have to know about that, but the system and the hardware has to deal with the fact that we may not be spawning perfectly aligned work. Okay. But it makes it inefficient. So if you're an efficiency programmer, you do care about that. If you're just trying to make this thing work, you don't. Yeah.
I'm trying to understand the organization. So like the block itself, is that what is split along 3 dimensions, or is it that each block is like conceptually linear and then like the grid itself is?
So both the grid and the block can be multidimensional, and they don't even have to be the same number of dimensions. So I can have, so again, it gets really weird. But I can have, typically they're the same dimensions. If I have a 2-dimensional block, I usually have a 2-dimensional grid because I'm cutting like this image that we're looking at, right? You're going to cut it up. We're not going to use 2-dimensional programming the first time we look at it, but that's an apt way to do it. But both of them can have X, Y, and Z components. So that's why the block ID X has a dot X and the thread ID X has a dot X, right? So they will all have corresponding dot Ys and dot Zs. And if you didn't make it multidimensional, those would just be 1. Okay, or their ID will be 0 because this will be the first one. Does that kind of make sense? So this will be a lot more intuitive when we look at a 2-dimensional program and show you how to spawn work, but you can futz with the dimensions in both spaces. You may also ask why 3. I mean, it's very possible that we have high dimensional data. This happens a lot in stuff that's not physical, but they just don't go beyond that because it's hard to visualize, dimensions beyond 3. And if you use 3, you capture most of the stuff that you might want to do. If you want to do higher dimensional stuff, then you're on your own. You have to create your own IDs in these higher dimensions. There's no like intrinsics for getting these from the GPU programming model. Okay. Yeah. Right here, then up here.
Why can't we have 3D computation structures like HBM?
What do you mean? How is H? Oh, like a stack? Yeah, I mean, you could, but it doesn't. You can look in hardware, you can sort of build whatever crazy nonsense you want, right? Like in the early days of system machines, we put operating systems in hardware, right? So you can do it, but it's not really a human. So you could conceptually say everything in the Z plane goes on another layer of a multi-layer chip. There isn't really, 3D die stack compute that's commercially viable at this point. But yeah, it's more of a conceptual thing than a physical thing, this 3 dimensions. But you could. Question here.
So when you said the 2D image could be a dot X and dot Y, was that for the thread ID?
That could be both. And naturally, usually you do, if you're going to do 1 2 dimensions, you do the other 2 dimensions too. But again, that's kind of on the CUDA programmers to decide. Okay, and you don't have to. You can fully compute a 2-dimensional problem with just 1 dimension, but now you have to figure out the offsets, right, to get like to the next row kind of thing. Instead of just knowing that I'm on row 1, row 2, naturally from your thread ID, you figure it out based on the linearized ID. Make sense? Yeah.
And how does what take to block?
Yeah, good question. So we'll see this again as we get into what happens after you code this up. But what the hardware will do is it will take every block and break it into warps. And those warps is what will end up being run on the hardware itself. So at this level, and at the highest levels of CUDA programming, there is no concept of a warp. You don't actually have to know that there even is a warp to write this code. But you do have to know that there is a block and a grid because you have to specify those things. Okay. And block sizing, like I said, becomes very important when we start using the Scratchpad because the Scratchpad is allocated on a per block basis. Okay. Other questions? These are all very good questions. For those of you who are sort of not quite sure what's going on, it'll probably become a little more clear, as we go through. All right, I'll sort of caveat here is that CUDA is not the only way to program these things. There's lots of other programming interfaces. I may touch on them a little bit in sort of the rest of the world lecture at some point, but CUDA is the most mature. It's certainly the most full-featured and the most used, so that's what we focus on in this class. All right, so here is maybe a visualization of what I was talking about with this programming model, where you've got, the whole program. So every GPU program needs a host. So when you compile your GPU programs, you'll have a main. That main will run on your host. And then you're going to have to basically run a bunch of commands on the CPU to set up stuff on the GPU, and then eventually, launch the kernel itself. So if I think about the number of threads in my system, and this is just a picture of a linear thread array, so forget about the n dimensions right now. I've got my serial code that's running on a CPU that's just one thread, sort of going through the code in the way that I normally would think of it going. And then eventually, once I've done enough work on the CPU to set up the GPU, I will trigger what we call a kernel spawn. Okay, this kernel spawn will call into drivers on the host machine that will eventually orchestrate all of the threads that you want spawned on the GPU. And at this point, I'm going to now have all of the threads that I wanted conceptually running on whatever GPU or collection of GPUs I have on my system. Okay, and you'll do this parallel part of the kernel. As I've said before, the CPU can go off and do something else if it wants during this time. It typically doesn't in a lot of programs. And then as soon as it's done, the control will transfer back to the CPU, usually through what we use as a memcopy. So we memcopy the data back. That ends up being a synchronous operation, which means that the CPU has to wait for the GPU to finish before the memcopy completes. And then the CPU gets that memory back in its own sort of memory space, does whatever it wants, and then maybe we're calling kernels in a loop, and then we go call another kernel again. And this time it's a different kernel with a different set of code. And the syntax here is weird, but you'll get used to it, where you have to do these triple less than, triple greater than signs. This tells the CUDA compiler that I want to spawn a kernel. It's a special symbol that's just for spawning CUDA kernels. And you give it arguments. The first two arguments we're going to look at is just the number of blocks and the number of threads. In reality, these are three-dimensional arguments, but for the first programs we'll look at, we'll just give them one dimension. And if you only specify one dimension, it'll assume that it's unit in Y and Z. So you'll just have a linear array of threads. And then I pass whatever arguments I coded up in my kernel. So when you write your kernel code, it'll look like a C function, and you'll be able to give it as many arguments as you want. And you'll pass that arguments list along with the level of parallelism that you want to run. And your program will generally flow this way. Okay, questions? All right, so thread blocks. Like I said before, we have to divide the kernel into chunks because, there's some features of the programming model and just good data parallel programming in general that really necessitates us to cut these things up. So we divide the kernel into chunks. These are called thread blocks. In the hardware, they're called cooperative thread arrays or CTAs. What does AMD call these things? Anyone know? Work groups. Okay. So AMD calls thread blocks work groups. Again, synonym. Doesn't mean anything. It's the exact same thing. The programmer specifies it. It's just like a subset of threads. Call them work groups. They call threads work items. NVIDIA calls them threads. So anyway, so basically it's this way to subdivide the sort of broader amount of parallelism that you're spawning in a kernel. Okay, so you divide the kernel into these chunks of threads. The threads within the thread block have special operations. As we'll see, they can synchronize very quickly. So there's hardware synchronization built into the machine to allow these things to barrier very quickly on each other. And they can share the on-chip scratchpad memory, which means that if thread 0 loads something into the on-chip scratchpad, then thread 7 in the same thread block can then read that value. That's not generally true among parallel thread blocks. Okay, so you have this sort of fast communication substrate for threads within the thread block, and you can also synchronize very quickly. Generally, among thread blocks, communication is much more expensive, and if you can avoid it by the way you code up your program, you generally don't communicate in between thread blocks. So yeah, the way that this usually happens is you let all the thread blocks finish, and then you just spawn another kernel, right? And then if they needed that data was written out to the global memory, and then they read it in again. Like I said, is some complex orchestration that you can do in sort of more advanced programs, but we won't touch on that too much in this class. So conceptually, it looks like this. My kernel has, let's say n thread blocks. So I have thread block 0, thread block 1, and then thread block n-1. Each of these individual thread blocks has 256 threads in them. So the individual thread IDs are through 255. And then when I spawn this and I run this sort of these 2 lines of code, every one of the threads and every one of these thread blocks is actually going to be touching different data, right? Because they're all going to be offset by whatever their block ID is. Okay, questions on this? No? Too simple, or you just don't know what's going on? Okay. All right, y.x, I said this before, so there's actually 3 dimensions. Like, it simplifies things for higher dimensional data. The hardware, as we'll get into, does linearize these. There isn't an actual 3-dimensional unit inside of it, as cool as that might sound. But it makes programming simpler if you actually have 2-dimensional data that maps naturally to it. So the simplest kernel we're going to look at first is a linear one. So this luminescence kernel we'll look at as our first 2D kernel, but our first linear kernel is vector add, the absolute simplest data parallel program that you can think of. I've got 2 vectors, each of them have some number of elements, and in this case, I really just want to add them together and then store the result. Where is that arrow going? You guys see that? This is the weirdest vector add I've ever seen. So I usually do these in PowerPoint and I save them in Keynote and they did that. That's random. So that shouldn't happen. Okay. Not doing it, trying to confuse. That arrow is supposed to go right here. Okay. So basically you're reading one element of A, one element of B, adding them together and storing them in C. That's the sort of basic computation. All right. So here is the shell of a C program that does this. So if I have vector add, this is a CPU version of the C program. This should not be intimidating to any of you. If it is, then reconsider taking this class, where I'm basically just passing in pointers to A, B, and C. I'm telling you how wide the vectors are inside the serial program. I've got a loop. I go through all of the and I add the 2 things together and store the C. And then from the main program, I then call this vector add. Okay. So this is just to run this on the CPU. To run this on the GPU, we're going to have to do a whole bunch of other stuff up here in the main program to set up the GPU to run. Okay, on CPU, you would allocate A and B. Well, so this is saying what you need to do still, even if you're running it on a CPU. So A, B, and C all need to be malloced, right? You need to have a malloc for these if you're doing this on a CPU. The _H here, because when we're dealing with 2 separate memory spaces, it helps a lot to name our pointers as either host or device. So you'll see a lot of this, naming convention in the book and in the slides where we have a pointer. If we know where the pointer points, we'll say in the pointer itself, okay, to help keep our heads straight, because there'll actually be different addresses, right? Like if you have A on the CPU, like the A array is on the CPU to begin with, and then you put it on the GPU, you'll have literally different pointers to that data to signify, which of those address spaces you want. And it's, more sane in the code to sort of write down _H and _D. Okay, so in a CPU, you do this, you'd allocate memory for these, then you'd read A and B from IO probably, or randomize it if you just don't care about what the program does. And then you just have some number of N elements that you sort of know you read from the file or whatever. So that's a sort of basic CPU program. So if I want to change that to now use the GPU, I have to do a few more extra steps. Okay, so I have, these are my, so this is my sort of vector add program. So I've got my main program doing all the stuff that it needs to do for the CPU. And now when I call vector add, instead of just having a simple for loop, I'm going to set up the GPU and then copy the data into the GPU, spawn the kernel, and then copy the data back. Okay. So I end up creating pointers for A device, B device, and C device, because I need all 3 of these arrays to live on the GPU's device memory, as well as the CPU's host memory. And then I need to sort of figure out, what the size of these things should be. And I do that by just, N is the size, and then each of them is going to be a float. Okay, so size of float. The first thing I need to do is allocate device memory. So there's going to be a special malloc call you'll need to use to allocate memory on the GPU. We'll look at that in a second. Then I launch the kernel. Then I copy the data back. So I will allocate space for A, B, and C. I will copy the data into A and B because those are the inputs. And then I won't do anything with C. I will just end up passing all 3 of those pointers to the kernel that I spawn. And then the GPU will then read from those 2 A and B device pointers that I allocated, and then write to that C device pointer that I allocated. And then at the end of it, I will then have to copy it back from the GPU, because after the GPU's done its work, the C array that matters lives in the GPU memory. So I need to do then mem copy that back into the CPU memory. So that way, when I return to my main program, the data is back on the CPU. Okay. Generally, you're going to need to take whatever useful information the GPU produces and copy it back to the CPU. If you've got a lot of intermediate results, like machine learning, for example, if you're just, going layer to layer and you've got activation outputs from one layer, for those of you who know, what that means, we've got outputs that are then activations to the next layer that the CPU doesn't care about. You don't have to copy those back and forth. Those can just live in the device memory. The only time you need to bring it back to the CPU is if you run out of space or if you actually need the result. So if you think about neural nets, you could sort of keep all the intermediate data as long as your capacity is big enough in the GPU and then only copy out what the end vector was for what the results should be. So there's concrete code to go with each of these statements. So all of this is run on the CPU. Okay, I haven't written anything yet that actually gets translated into GPU instructions when I'm talking about this stuff. All of this is device driver stuff inside the CPU that's going to, allocate and orchestrate stuff on the GPU. So the basics of how this works, and this is a picture from, I think, the programming manual or the PTX manual or something, some kind of manual from NVIDIA, that again is sort of just giving you maybe a more colorful picture of generally how these things work. And we'll sort of build up this programming model as we look at different memory spaces. So each thread is going to have its own register space. And what that means is, when I have local variables inside a thread, other threads can't read those, right? So if inside my GPU code, I say int x equals 5 or int x equals thread ID, then other threads won't be able to read x because that's going to end up living in my registers. Similar to the way that CPU registers work, right? If you've done CPU programming, you can't share your registers. If you load into R1 in one thread, thread 2 can't read R1. Your R1, it has to read its own. So the programming model, every thread has unique identifiers. In this particular instance, we're saying that it's, what are we doing here? So this is basically a two-dimensional thing. And so we've got two blocks and there's X and Y. So these are the XY coordinates here in this example. And so if we launch a 2-block grid, okay, that has 2 threads in each block, then the XY block dimensions are going to be 0, 0, and 1, 0. And then the XY thread dimensions, so this is X, this is Y, this is X, this is Y, are going to be 0, 0, and 1, 0, right? And that the Y dimensions aren't changing because in this example, we're only launching a linear array, okay? So there'll be 2 threads in each of our blocks. Each of our threads will have their own thread private registers. And as you can imagine, once we start looking at more advanced programs, each block will actually have access to the scratch that they can share among the threads. But that's a conversation for a later date. Each of these threads will have access to what we call global memory. This is the GPU's device memory. So the HBM, the GDDR5 that's on the card itself, that's what NVIDIA calls the global memory space. It's where the A and B pointers were allocated when I did that code on the CPU to allocate them on the GPU side. And it's where C lives. So, sort of global reads and writes will go all the way out to that memory. There's optionally caches in the way here, but from the programming model perspective, you don't see the caches, right? This is just from the perspective of the programming model. Questions so far? And then there's an interface to basically take that global memory back and forth to the host. That's what the CUDA mem copies do. It copies stuff. It basically initiates a bunch of stuff that will initiate PCIe transfers if you've got PCIe-based GPUs, or NVLink transfers, or whatever, however you've sort of connected your host to your GPU. Okay, so every thread has read-write access to global memory, and yeah, discrete GPUs. This is not coherent, right? There's no, if I write to the A array in the GPU, the A array in the CPU does not get updated, right? I have to manually copy that back. There's a hand over here. Yeah.
In the integrated GPU, do we have to do the copy?
Yeah, in the integrated GPU, no. So in the integrated GPU, you will use usually a special allocation that's on pinned memory. So who knows what pinned memory is? What's pinned memory?
It's like the memory is like actually residing in the CPU. So every time like the device runs to it, actually goes through like the PCI.
Okay, maybe, but let's ignore GPUs for a minute. Pin memory exists in CPUs, like with no GPU element. So what does pin memory mean? Yeah.
Does that mean it doesn't get paged out?
It doesn't get swapped out. Because if I had something that, the GPU wants to read or write that's actually on disk. Like that's a disaster. Like you think going over PCIe is slow, go over SCSI or whatever, or SATA to go to a data bus to a spinning disk or even an SSD, like your life's over. So pinning the memory says that I am never going to page out this page in the CPU. So it will always be in memory. I can't swap it out. It effectively, is always going to be physically in the CPU memory. So if you're doing an integrated part, then when you call this special malloc, it'll pin the memory so that way it won't get paged out on you by accident by the CPU. And then the GPU and CPU can both talk to that same page. Okay, but again, this is usually less efficient because the GPU will have different demands. But yes, if you're using the integrated part, you don't have to do the copy. Okay, but you still have to do a careful allocation to make sure that the GPU can read this page.
So the programmer need to know if it's a dedicated GPU or a discrete GPU.
Yes, the programmer will need to know that. Yep. Good question. Other questions? Yeah.
So the host is just the CPU that actually has like the CUDA.h and like C code, and then it translates to, it knows that it needs to copy data over from the host CPU to the GPU to let it run and actually process, and then it'll take the memory back to the host.
Yep. Yep, that's right. So the CPU, your program was compiled on the CPU. We'll talk about the binaries for the program itself. Like part of the binary is your CPU ISA, which is usually x86, and then part of the binary is a special ISA that gets run on the GPU. So they will work together. Does that answer your question? Yeah.
Oh, so the scratch pad, so does each block have its own instance of a scratch pad then?
Logically, yes. Physically, no. So the scratch pads, and we'll get into this. Every core, every SM NVIDIA calls it, has a fixed scratch pad size. And we'll see that you can assign multiple blocks to the same core. And what will happen is they'll cut up that physical scratch pad among the blocks that are co-scheduled on the core. So from the programmer's perspective, yes, they have their own individual, each block has their own little scratch pad that no one else can touch. Physically, it's actually going to be a shared structure that all of the concurrently running blocks will have access to. And its size can vary. So, again, this is kind of a trade-off thing, but if I want to use a lot of scratch pad, it may mean that I can run fewer blocks because I don't have enough scratch pad to, facilitate lots of blocks. So there's going to be these weird kind of trade-offs that we'll have to deal with when we start dealing with the scratch pad. Does that make sense? Yeah. But from a programmer's perspective, it's wholly yours. Okay, other questions? Good question. Yep.
So we also have to make sure that every block goes to a different code in order to maximize scratch pad usage.
Yeah, and you actually have no control over that. When you spawn the grid, you don't tell it what core to put it to. So there's internal systems that will be as greedy as possible. So there's like internal schedulers that will take your blocks and try to spray them. The way that it works is it sprays the blocks across cores first, and then once it's got at least one block in every core, then it will start stacking them. And the reason is throughput, right? If I want to bring in as much compute as I can by lighting up as many cores as I can, and then as soon as I've got them all lit up, I start stacking them. Make sense? Right. And that only matters if you don't have enough work, right? Typically, there's so many threads that you're putting as much work as you possibly can on these things to keep them busy. Okay, good question. Other questions? Another one? Yep.
There's private memory inside global memory as well, right?
Okay, so yes, we will talk about that. So there is something called local memory. So the register space is private, right? Now, what happens if you run out of register space on a CPU? What do you have to do? Spill to what? A stack, right? Spills and fills from the stack. This will happen in GPUs too. Okay, you'll have to spill and fill from the stack if you run out of registers. That stack space it doesn't go to global memory. It goes to a special subset of the memory address space that is thread local. And again, we're sort of getting into something that's a little bit more complex, but yeah, there will be a fraction of stuff that it'll be backed up by the HBM, but from the programmer's perspective, logically is thread private. Make sense? You have a question here.
So if a block size is limited, and let's say the program is such where multiple threads want to share some data, but you cannot fit all the threads in one block. So there is no way to ensure.
Yeah. Oh, okay. So that's there's no way to make that work. So you can make it work, but you have to then those threads would have to communicate through a higher level of memory. And that's going to be naturally inefficient. So if you face such a problem where you could not design the algorithm around this, then a typical way to handle it is to do it hierarchically. So I sort of communicate as much as I can within the thread block. And then instead of having all of them try to talk to all of them in the other thread block I need, I just have a single sort of signal that I've aggregated from. So if you can kind of change the algorithm to make a hierarchical communication, it makes it much more efficient. But if you need to communicate across more threads than the thread block has, then there's no way other than sort of losing this efficiency. Usually that's not true. Like if you thought hard enough, you probably could re-architect the algorithm of the program, maybe even by having each thread do more than one thread's worth of work, for example, right? Because you can always have a loop inside your thread and say, like, I'm going to do the work that I logically wanted thread 0 to do, and then I'm going to do the work that I logically wanted thread 500 to do. And you can pack the whole program into one thread block, but it's going to be serialized, right, in a loop kind of thing. Does that make sense? So it's sort of up to the programmer to, think about how to either change the algorithm itself or change the structure of the parallelism to make that communication work. Okay, good question. Other questions? Yeah.
So how exactly is the hierarchical structure of the memory organized in the GPU? Like, is there, like, what are the oversubscription ratios when you go from register to global memory to higher levels of memory?
Are you talking about relative capacities?
Yes, because that would determine how inefficient it would be, right?
Well, that doesn't determine the efficiency. The efficiency is determined by their connectivity and cost of synchronization and how many taps there are on these buses, et cetera, or interconnects. Let's delay that till we start talking about the details of the memory system, because maybe that'll make it a bit more clear. Size-wise, GPUs have tons of registers. The register file space is actually bigger than the cache, right? Is not the case with CPUs. Even if you're doing, register renaming, if you took 565, we've got a lot more physical registers than architectural registers. Your cache is still way bigger. On the GPU, the L1 cache is actually smaller than the size of the physical register capacity. Why? Well, because I want to pack as many threads as possible on this thing. And so to get more threads, I need more registers. So a lot of the SRAM actually ends up going to the register file. So you actually have this kind of inversion in the size of these storage structures versus what you'd see typically in a CPU, which is kind of interesting. Other questions? Yeah. Oh, right here first, yeah.
What's the typical number of registers per a thread?
Good question. So there's a maximum number. So the ISA itself can only encode 256 architectural registers. And again, this is machine dependent, but this is the typical CUDA flow because there's only so many bits in the instruction encoding, right, for every register that you want to touch. And there is no renaming like on CPUs because that's expensive. So there is a physical limitation that every thread can only have 256 at most. So if you had a program where you had more threads, then it's going to have to more registers and had demand for more than 256 registers, then that every thread is going to have to spill and fill to deal with that fact. Okay, so there is a finite limit on how many, but that can vary, right? So again, it's like a trade-off between how much I give each thread versus how many threads I can have. And CUDA programmers play this game a lot of like, okay, if I use all 256 registers, now I can only do 200 threads in the core. And if I used half as many registers, then I can do 400 threads in the core. So it's sort of fungible in that way. So that way you can sort of distribute the parallelism.
So you basically always, like the programmer chooses this is the number of threads I'm going to spawn. And because of that, the physical number of registers, because it's a fixed value of the GPU, it limits that this is the number of registers of each thread.
That's a good question. And typically no. So typically the decision on register usage happens when? When do you think?
Runtime.
No. Register usage.
Is it just like hard coded that this thread can only have these set of registers and that's it?
In a way, but who determines how many registers each thread is going to get?
Hardware designer?
No. Well, the maximum limit, yes, but for any individual piece of code, which element in the system determines how many registers the thread's going to get? Not the OS. Compiler. Who's taking compiler's class? Register allocation, coloring, graph coloring. You guys do this kind of things? This is determined statically. Right? That all happens in a GPU too, right? It still looks at the program and tries to register allocate. So when I compile the program, it says how many registers I need. And you can end up in these weird situations where, like, I compile the program, so the determination on number of registers is done at compile time. And the determination of number of threads is done at runtime. So you might end up in a situation where the compiler said, I want 256 threads, right, in each register. And then the programmer said, I want my block to be 1024 wide. And then you launch it on a cheap GPU and it doesn't have enough registers to store one block and it'll blow up and die and say, look, you've got to fix this. And you can fix this by just going to the compiler and saying, please only give each thread 16 registers or something. And then you'll recompile the code and it'll all work, but it'll have to spill and fill. So you get a lot more memory accesses instead of register allocations. Make sense? Good question. You have another one. Yep.
How many physical registers are there?
It depends on the generation. So thread wise, it's usually like 40,000 32-bit registers is what they claim. These are actually vector registers, but I don't remember the exact numbers. It's tens of thousands, I think, of physical registers on each SM. You can look these up. I could do it for, it's not, I don't have it on top of my head, but that's sort of the range. Yeah.
So for integrated GPUs,
Yeah.
since the GPU and the CPU will have different page sizes, how do we take care of that?
So they don't. So you usually, if you're doing the integrated GPU, they will have the same page size because otherwise the whole virtual memory system collapses.
Yeah.
So again, another reason why it's less efficient to bolt them together because you've got to deal with 4K pages. I may have misquoted that register number. I need to double check that. I'll post a Piazza. I'll show you guys the link. I think it's in the slide somewhere. I just forget the actual physical number. Yeah.
What's the difference between physical and architectural registers?
Okay. Who wants to field that question? What's the difference between a physical register and an architectural register? 565 pop quiz. Somebody else. Yes, up here.
Architectural registers are registers that your code can, like the logical registers that your code can address physical registers, like what's on the chip, and depending on what your hard setting you could assign logical registers.
So physical registers are intuitive, like literally, this is the storage that's on the chip. Architectural registers are, you're sort of on point there, but what's a little bit more precisely what's going on with architectural registers? Yeah.
They're specified by the ISA.
The ISA. So those are the ISA visible registers. So x86 is a prime example of like, it's an ancient ISA and it really doesn't have that many registers, right? If you look, I think, what's the number? It's like 1632 or something. It's something super small, right? Because it's been around forever. But CPUs don't just have 16 registers. They're renaming them under the hood for you with, register renaming because they have many more physical registers. So a physical register is the actual register itself in the hardware. And an architectural register is what the ISA sees. Okay, architectural is because instruction set architecture. That's where the name architectural sort of stems from. Okay, good question. Other questions? Don't be afraid to ask these kind of questions. If you had the question, probably other people also were sort of trying to remember the sort of fire hose you drank from in 565. Okay. All right. So how do we interface with this from real code? You guys are going to be asked to do this. So CUDA-malloc, that is the API you're going to use. So you're going to compile these programs with, there's a shared object from NVIDIA that has these definitions of these interfaces in it. CUDA-malloc will give you a pointer to something in this global memory space, and then CUDA-free does essentially the same thing, or the reverse of that. It basically frees it just like malloc and free typically do. So these operate a lot like malloc and free. When you start using them, if you've never used them before, they're a little bit different because malloc gives you back the pointer that you wanted. CUDA-malloc doesn't do that. CUDA-malloc gives you back basically an error code if something went wrong. So that means that the pointer isn't the return value from the function. You have to like pass the function the pointer, and then it overwrites it inside of it. Okay. Hopefully, again, sort of basic C pointer stuff that maybe you need to review a little bit when you use these things. So you can't just go like, float star equals CUDA-malloc blah. That won't work, right? Because you'll assign the compiler will complain. So those are the two basic things you're going to do. And then there's an API called CUDA-memcopy, which will take these pointers. It will know, what pointers go where. You can give it a direction. I think the direction is now optional. And when I say direction, I mean like, am I going from host to device or am I going from device to host? I think it's smart enough now to know what the pointer is, but you may still have to give it to it, at least in the older APIs you did. And that's what the book says anyway. So basically it's got 4 parameters. Your pointer to your source, pointer to your destination, pointer to your source, just like a normal mem copy, number of bytes you want to copy, just like a normal mem copy. And then you tell it the direction, tell it whether I'm going back over to the device or back from the device. When I call CUDA mem copy, this is synchronous. So this is important because if you're just running your CPU program and you're sort of going through it, right, and you're single stepping, and you get it to your kernel call, and then you single step it, it'll come back right away. And be like, oh, even if that kernel was supposed to take 3 minutes on your GPU, it just like the call to that kernel comes back right away because it's asynchronous. Okay, so kernel calls are asynchronous. Behind the scenes, they're queuing these things up, and then the mem copy call to copy the data back from the device is synchronous. So you'll basically call the kernel spawn, the CPU will immediately sort of queue that up in some internal queuing system, and then you'll go to the mem copy that will want to bring the data back, the thing the GPU actually produced, and then it will wait there. And it'll wait there for the GPU to finish its business and then copy back the data that you hope is there if your program worked correctly, yes.
It's synchronous, but it's non-blocking, right?
No, it's blocking. It's synchronous and blocking, yeah. There is a non-blocking version if you really want to orchestrate things and deal with synchronization yourself. Yeah, it just depends. If you had an arbitrarily complex program, you might want to do that. Usually you don't need to. Like usually you just call CUDA mem copy right before you actually need the data from the GPU. But again, you could do some clever overlapping if you were clever about async copies, etc. But the basic programs, it's usually spawn your kernel and then synchronously copy back and sort of wait for it to be done. And the CPU is free to do other stuff, right? So if I want to like spawn my kernel and then go call 17 CPU functions before I do the mem copy back, that's perfectly fine. Now, what you can't do is read anything that you think the GPU had produced, right? You can't just like not call mem copy and then start reading from, if you try to read from the device pointers, it's going to segfault because it's going to try to translate it in the CPU. And it's going to be like, I don't know what this is. I never allocated this thing. Go away. If you try to read from the host pointer that hasn't had the CUDA mem copy come back into it yet, then you'll just get trash data because it'll just be the empty data you allocated originally. Okay, so you're going to have to wait for that mem copy to complete to actually do anything with the data. So you use the synchronous mem copy to do that. Yes.
Does do kernels do checking to make sure you're accessing valid addresses or?
Yes, they can segfault.
Okay.
And again, it's not like robust Java out of bounds checking or any of these kind of fancy higher, like it's just C, right? So if it tried to translate something, it's like, I don't know where this page is, it's going to segfault. It'll do the exact same thing that your C program would do if you try to access invalid memory. And if you allocated something and never wrote to it properly, it's just going to keep going, right? And be like, oh yeah, okay, I guess you want this data. You're going to walk off the end of arrays and all of that stuff, just like a normal C program, okay? So it's no easier. I mean, it's only harder than sort of doing, it's strictly harder than doing this on the CPU, but it's not that bad. You can debug too. There's a debug utility called CUDA GDB, and you can fire that up and you can put breakpoints in your CUDA program. And it starts to get a bit hairy, right? Because like, imagine trying to put breakpoints in a kernel with 10,000 concurrently executing threads, right? If you don't say what thread you want that breakpoint to happen on, then it'll happen on all the threads, and you'll get like every single one of them will hit the breakpoint like all at the same time. So it gets tricky to debug these things. But it is doable, and there are sort of pretty good tools to help work you through it. Other questions? Okay, yeah, here.
Yeah, so when it comes to things like speculative execution, that if the CPU makes a mistake, it has to roll back. That becomes very difficult for the GPU as well, right?
So you're talking about if the CPU like makes a branch prediction, and then has to roll things back. So, okay. So how could this happen? So if I have an if statement in my CPU, and then that's a predicate for essentially triggering the kernel, right? And then you started to run the kernel code. Sorry, the code that spawns the kernel. So again, this is going to be a whole bunch of operating system stuff. You know, this is all going to end up like when you go to spawn the kernel, it's gonna go down into like OS level, kernel level privileges, right? And it's gonna blow away a lot of that. Like it's gonna forcibly wait because it's gonna have to switch modes from user mode to kernel mode, and that's gonna put the brakes on your like your CPU is not going to be allowed to bleed into these in the out of order execution in the way that you're sort of thinking of. But I mean, it's a good intuition that if I had it like huge out of order and like it like speculatively started to spawn the kernel, like I can't roll back the kernel spawn, right? That's gone, man. It's already running. No, your CPU, there are guard mechanisms to make sure that your speculative X isn't gonna cause you to erroneously kick off kernels on the GPU. But it's a good intuition. Yeah, question.
So do GPUs then support precise interrupts, or are they?
Good question. No, so they didn't used to. The newest ones, I don't know if they've actually got support for precise interrupts or not. Because there's no out of order execution, but there's still out of order completion, right? And unless you have essentially a reorder buffer-like structure where you're keeping and forcing an order, which is overhead that GPUs typically don't want to pay, enforcing precise exceptions is tricky. I think that the way that they usually handle this is that if you compile a program in debug, it will put a bunch of stuff in there to try to make sure that your exceptions can be precise. It will slow things down intentionally. And then if you don't add those extra software markers, you won't get precise exceptions. I don't know that for certain, but that's a good question. Historically, no, there's been imprecise exceptions. So you put your breakpoint in there, and the state of the machine may actually be slightly different than what it should be based on where your breakpoint is because the exception was imprecise. Okay, good question. Yep, one more.
What about integrated GPUs?
Yeah.
They just bite the bullet and say we're gonna sacrifice performance for precise interrupts.
I don't think there's really any difference. So integrated GPUs are usually like the poor children of the discrete ones, right? They create the architecture for the discrete chip. And then, I mean, this is like, they create the flagship architecture and they just reuse it in the integrated parts. I mean, the Apple is probably an exception because this is the flagship chip. But for primarily discrete GPU companies, usually they're just iterations of the architectures that they, like AMD, for example, that they put in the discrete chips. Modulo all the stuff they have to do to glue them together. Okay, but the internal guts of the core is usually the same. All right, one more.
What if you already have coherence in your GPU, like AMD? Can't you very easily support a precise interrupts then?
If you have machinery to support, well, coherence and precise interrupts are different things.
Yeah.
Right? Coherence is talking about, multiple caches and making sure that there's relativity among those multiple caches. Precise interrupts mean that that you're sort of stopped at a particular point in the program, right? Just inherently whenever the interrupt occurs, and you didn't bleed through, right, to any other instruction. Those two things are sort of orthogonal. So I don't know that adding coherence, paying for coherence is way more expensive than paying for precise exceptions. Mm-hmm. So if you've already paid the coherence cost, maybe adding the precise exception is a small overhead on top of that. So again, maybe they have mechanisms for precise exceptions. I don't know. And the current GPUs may, I don't know if Hopper has precise exceptions or not. I can look into that. It's a good question. But historically, no. Like the early GPUs, early CUDA did not support precise exceptions. Okay. Other questions? What else? Oh, good. I got to the code. All right. So here is the CPU code. So this is literally what you'd have to write if you wanted to do this on the GPU. So here we've got, the API calls. So we've basically got a CUDA malloc. And some of these are nasty looking, right? Like you've got to cast these things to a boy pointer and you got to pass it the malloc, you actually have to give it the pointer, right? So CUDA malloc, you have to give it the address of the pointer itself that it will fill inside in the API. Again, this is sort of basic C stuff. Go back and look at 264 if this sort of confuses you. And then these are the mem copies. This is what actually moves the data in. And then we malloc the space for C. We don't actually write to it. And then we do a CUDA mem copy at the end, to bring the stuff back over. And I'm sort of skipping the part 2, which is the kernel invocation. This is all the memory management code that you'll need to orchestrate to move stuff back and forth to the GPU. Let's see. Yeah, let's just talk about this very quickly before we end for today. So this is the actual GPU code. Okay, so when you mark a function with this global keyword, so this underscore underscore global underscore underscore, the compiler knows that this can be called and run on the GPU, and it looks just like any other normal C function, except inside this global function, these intrinsics, this thread IDX, block IDX, etc., will be there. So you'll be able to use those inside your code. So now that loop that I had when I was doing my vector add on the CPU, I basically just parallelized it to run it on the GPU. How did I parallelize it? Well, I computed, instead of having the loop index I just go one by one every iteration, I am now having all of my side-by-side threads do each iteration of the loop. This is the textbook definition of data parallelism. And then I just have one single operation, okay, in every thread. So this is not a very compute dense kernel, right? This is not a very efficient kernel, but it is super parallel where every thread is basically just going to go and do the reads to the two A and B values, suck them into the core, add them together, and then write it back out to the C. And then I also have this weird little thing here. So what is this? And what is this doing? Yes.
You're gonna have inevitably, you're gonna have more threads than you have data.
Yep.
So you need to make sure you're not doing things on those threads that don't have data.
Right. So exactly. So if I ended up spawning a grid that wasn't the exact dimensions of my grid size, which is possible, right? Because those are runtime values that I set. I would basically get seg faults if I tried to run this code because I'd have more threads than I actually had data to use. So to prevent that from happening, I add this if statement. And so now every thread is going to go in here and check to see if my individual thread ID is actually within the bounds of these arrays that I want to add together. And if it is, I'll do the math. And if it isn't, I'll just quit. So the threads that the over parallelism that you created just comes in, tests its thread ID, and disappears. It doesn't do any useful work. But the program doesn't crash because we added this little guard. And then the CPU side of this to actually call. So this is the code itself. This is what runs on the GPU. The code that actually kicks off the kernel that you shove in the middle of all that memory management stuff from the previous slide looks like this, where I'm essentially just calling it with the, this corresponds to this corresponds to this, etc. And I've specified the parallelism. So this is saying how big my block is. My block is 256 threads. And then I'm just using this ceiling operation. Again, this is why I need that if condition in there, because I need to spawn a finite number of I can't spawn a fractional thread block. I have to spawn an integer number of thread blocks. So I take the total size of my big vectors n, and I divide that by 256 to figure out how many thread blocks I need, because each thread block has 256 threads in it. And I take the ceiling because if I have 257 threads, I'll need 2 thread blocks, okay? Because I need to cover that one thread that's sort of fallen off the end of the first thread block. And so the ceiling will give you that integer number. And then this if statement in here will protect you from falling off the end of the arrays for all the rest of the threads in that block that you launched, okay? Last question, we're 4 minutes over time. What? Sorry, I like the questions. Go on.
This kernel is memory bound, right?
This kernel is memory bound, yes. Because if there's enough threads here, if you can get enough threads in the thing, you're basically doing one operation for every 3 memory accesses. Yes.
If you have a bunch of these one after another, how do you stack them so you're not repeatedly passing control flow between the GPU and the CPU and the GPU and the CPU?
So if I stack, if I put vector add, vector add, vector add, vector add.
Yeah.
So they will basically run in 2 logical threads of execution. So the CPU does when it calls this kernel, it'll push the kernel spawn into a queue. So the first time it calls a kernel, it pushes in a FIFO queue. The next kernel will just be right behind the other kernel in the FIFO queue. And then it'll just keep stacking that queue. So it can spawn 1,000 kernels. They'll sit in some software data structure queued up. And then it's not until I call the memcopy that I drain the queue and then get the memcopy back to actually, synchronize the CPU. Okay, good question. All right, I have to leave you here for today. Come back next week, and we'll talk more. All right, thanks a lot. Have a good weekend. Start your programming assignment, please, and use Piazza. Okay, the TA and I will be looking at it. make sure that all the systems that we say should work. And we'll go from there. Thank you.